All right, let's go ahead and get started. I want to welcome you back to Unit 4, the periodic table. This is the final screencast for this unit, and I thought a good place to end here is to look at some questions that are going to test our knowledge, test our understanding of the periodic table, and prepare us for the exam. So, if you don't have a periodic table in front of you, go ahead and pause the video and we will get started. Number 1 says, what happens to the atomic radius size as you move across a period? So remember, as we move from left to right across a period, what's happening is that the atomic radius size gets smaller. It does so because of the fact that you are increasing the number of protons in the nucleus and simultaneously increasing the electrons in the periphery, thus increasing the nuclear charge, the attractive force between protons and neutrons. As that nuclear charge increases, of course, atomic radius size decreases, right? All right, so that's number 1. Let's take a look at the second one. Number 2 says, what happens to electronegativity as you move across a period? So this time we're looking at electronegativity and the trends of electronegativity. Let's pick a specific period. Let's take a look at period number 2. We have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And we want to know what's happening to electronegativity. Remember, the trend is left to right, electronegativity increases. Now, remember also, however, that neon doesn't have an electronegativity. It doesn't want to pull electrons from anything else because it has the octet. But nonetheless, our answer remains the same. What happens to the electronegativity as you move across the period? It increases. So that takes care of number 2. Let's look at number 3. What happens to the ionization energy as you move across the period? Well, ionization energy mirrors exactly electronegativity. It increases as well. In fact, while there's no electronegativity for the noble gases, there is a first ionization energy. It's rather high, but there is an ionization energy for the noble gases. So to answer the question, what happens to ionization energy as you move across a period? The answer is ionization energy is going to increase. So that takes care of number 3. Let's take a look at number 4. Why does atomic radius size decrease as you move across a period? Well, we've already answered that, but we'll talk a little bit about that once more. As you move from left to right, atomic radius size is going to decrease. It's going to decrease because of the fact that you're increasing the number of protons and electrons, thus increasing the nuclear charge, that attractive force. So as you move left to right, if you increase the attractive force from the nucleus out, say, towards or through the electrons, it's going to have a tendency to make the distance between protons and electrons in the periphery shorter and shorter and shorter. So the atoms get smaller and smaller and smaller. So that takes care of number 4. Let's look at number 5. Why does atomic radius size increase as you move down a family? There's 2 important reasons for this. The first is that as you move down a family, let's take the first alkali metal family, for example, hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. As you move down that family or down that group, you're increasing the number of electrons, but you're adding electrons to higher and higher and higher main energy levels, unlike when you went across a row. So if you go from hydrogen to lithium, for example, you went from first main energy level to second main energy level. If you go to sodium, to third main energy level, potassium, fourth main energy level, and so forth, right? So the point is this: you are adding electrons as you move down row to row to row to higher and higher main energy levels, which are just naturally further away from the nucleus. Just makes sense that they would be bigger. But there's another reason, and that reason is called shielding. As you move further and further and further away from the nucleus, the electrons on the very periphery, the very farthest electrons away from the nucleus, are shielded from the nuclear charge by intervening electrons. So if we take, for example, francium. Francium is in the 7th main energy level. Those electrons are going to be shielded from the nucleus by the electrons in the 6th main energy levels, 5th main energy level, 4th, 3rd, 2nd, and even the 1st main energy level. So 2 reasons why, as you move down a family or a group, the atomic radius size gets bigger. That'll take care of number 5. Let's look at number 6. What is shielding and what does this help to explain? We've just talked about that. Again, shielding is the interference of the attractive force by intervening electrons. And electrons in intermediate shells, the atomic radius is going to be lengthened. It's going to be increased because of the fact that those intermediate or intervening electrons are preventing the full force, the full attractive force of the nuclear charge. And this helps to explain why the atomic radius size increases as you move down a family or a group. That's number 6. Number 7, what's the largest atom on the periodic table? That's pretty straightforward. It's the one that's lowest and to the right. It's francium. Okay, so francium would be the largest atom on the periodic table. What is the smallest atom on the periodic table? Well, you go to the opposite end, up and to the right. So it would be helium. Helium would be the smallest atom on the periodic table. So that's number 8. Number 9, what atom has the highest electronegativity on the periodic table? Now be careful here. The trend is up and to the right, but remember, noble gases don't have electronegativities. So the highest electronegativity is a halogen in the 17th column. It's the highest one in that column. It would be fluorine. So fluorine has the highest electronegativity. That's number 9. Number 10. Name 2 elements that have similar physical and chemical properties to silicon. Well, find silicon on the periodic table. It's number 14. Remember that anything that has that number of valence electrons, right? Anything that has that number of valence electrons, in this case, that would be carbon, germanium, tin, lead. Those are going to have similar physical and chemical characteristics. Let's go over valence electrons one more time. Everything in the first column, that's hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, are going to have one valence electron. One electron in the outermost highest energy level, right? The second main energy level would be beryllium, magnesium, calcium, strontium, barium, and radium. Those have two electrons, or 2 valence electrons. These are electrons, by the way, that we'll learn are available for bonding. Now the transition metals are going to be kind of a mishmash, so we're going to skip over those. We're going to go all the way to column 13. Boron, aluminum, gallium, indium, and thallium. Those have 3 valence electrons. Carbon's group has 4, nitrogen's group has 5, oxygen's group has 6, the halogens have 7, and the noble gases have 8. Some people say 0 because since they're the electrons available for bonding and the noble gases do not bond with anything else, they say that there's 0. So keep in mind that you can tell how many valence electrons there are by looking at the family or group that it's in. All right, so that takes care of number 10. Let's look at number 11. Why does the atomic radius size decrease as you move from left to right in the period, but increase in size as you move down a family? We've already looked at this, but we'll say it one more time. As you move from left to right, atomic radius size decreases because the nuclear charge increases. You have more and more protons and more electrons. But as you move down a family or group, you're adding electrons to the subsequently higher and higher main energy levels, and you also have the phenomenon of shielding. So those 2 reasons explain why atomic radius size gets bigger as you move down a family or a group. Let's look at number 12. What's the difference between electronegativity and first ionization energy? Electronegativity is the energy required, or the tendency rather, of an atom to pull electrons from surrounding atoms. If I, for example, have an oxygen-hydrogen bond, oxygen is what we call electronegative. It pulls the energy, the electrons in that bond, shown as a dash here, between the oxygen and the hydrogen. It pulls it away, pulls the electrons away from the oxygen. First ionization energy is the energy required to remove a single electron. So for example, if I have sodium, sodium is a neutral element that has 11 electrons, one of which is valence. Let me just denote that with a little dot. If I add energy, I'll just use an E to add to denote energy. I get an ion plus the electron that I've extracted, right? So that then is going to be the energy required. That's the first ionization energy. So that's the difference between electronegativity and first ionization energy. Let's look at number 13. An element has this electron configuration 1s2, 2s2, 2p6, 3s1. What block of the periodic table is this element located in? So remember that we're going to be looking at the last electron, right? We're going to be looking at electron number, or the very last one. That would be this one right here. Now we're being asked what block it's in, so that means, remember there's only 4 blocks, S, P, D, and F. Clearly, this is the S block, right? So the answer would be S block of the periodic table. So the answer would be S block. That's number 13. Number 14, what family or group is this element located in? Well, look to the last main energy level. I'm sorry, the family or group, it's 3s1, so that means it's the first of the 2 in the S block. So what family or group? We would call that the alkali metals. So this is an alkali metal. What period then? Now we get to the question I was answering before. What period is this element located in? It's the main energy level. Obviously, it's a 3, so it's the third main energy level. So what period is it located in? It's the third main energy level. So there we go. That's number 15. Number 16. What is the name of this element? Well, let's add up electrons. 2, 2, 6. That's 10 right there, plus 1 more. That's 11. That would make it sodium. So this is sodium, right? This would be sodium. Third main energy level, S block, first column, the alkali metals. Number 17. Which is larger, a magnesium atom or a magnesium ion? Remember, magnesium is on the left side of the periodic table. It has a tendency to lose electrons, so the ion would be smaller. It's Mg plus 2, so the magnesium atom would be larger because the ion's smaller on the left-hand side. On the right-hand side, let's look at number 18 now. Number 18, which is larger, an oxygen atom or an oxygen ion? The ion is bigger because it has 2 more electrons than the atom from which it came. So this time the ion is larger, right? The ion is larger. That's number 18. Number 19, which is more reactive, cesium or francium? So if we go to the first column of the periodic table, remember reactivity increases as I move down the periodic table. It's going to increase. So the one that's lower is going to be the more reactive. In this case, it would be francium. Okay. By the way, francium is extremely reactive. And let's end this with a challenge question. Number 20 says, the first ionization energy for magnesium is 2,234 kilojoules per mole. And the second ionization energy is 2,471 kilojoules per mole. We expected it to be larger, which is somewhat higher. Why is the third ionization energy, which is 12,503 kilojoules per mole, so much higher than the first and the second ionization energies? Well, the answer has to do with the number of valence electrons. Remember that magnesium is in the second column. That means 2 valence electrons. To remove the first one requires this much energy, 2,234 kilojoules per mole. To remove the second one is going to require more. But now that you've removed those 2 electrons, you've removed the outermost electrons, and you're going to now be removing electrons not from the third main energy level, but from the second main energy level. That's going to be a lot harder to do. In fact, it's going to require almost 10 times more energy, 12,503 kilojoules per mole to do. So that's our challenge question. If you try to extract electrons from any inner main energy level, you better have a lot of energy to do it with, because it's going to not want that to happen. Folks, that'll do it for this challenge question. That'll do it for this unit. I'll see you in the next one. Thanks. Bye-bye.